Welcome back, everyone. Today, I want to talk about something that many engineers overlook, and that's the question of why ISIS still exists when OSPF is already there. Most engineers learn OSPF first. Some pick up EIGRP along the way. Service provider engineers gravitate toward ISIS. But here's the real question. If OSPF already does the job, why does ISIS still survive in modern networks? And I want to be clear, this is not a protocol question. This is a design question. And that distinction matters a lot. So let's start from the beginning. What is an IGP and why does it matter architecturally? An IGP, Interior Gateway Protocol, is the routing protocol that operates inside a single organization. One company, one service provider, one enterprise. It does 5 critical things. First, it operates inside one administrative domain. Second, it provides internal reachability. Every router knows how to reach every subnet. Third, it feeds PGP because PGP relies on IGP for next hop reachability. Fourth, it supports fast convergence, so the network reacts quickly to failures. And fifth, it scales to hundreds or even thousands of routers. Think of the IGP as the internal nervous system of your network. If it's slow, the body reacts slowly. If it's unstable, the entire system shakes. If it doesn't scale, growth becomes painful. Now, what breaks first as the network scales? 4 things: flooding overhead, LSDB size, SPF recalculation cost, and feature extensibility limits. Let me explain each one clearly. Flooding overhead. In link state protocols, every topology change must be flooded everywhere within scope. More routers means more flooding. More flooding means more CPU and bandwidth consumption. LSDB size. Every router stores a complete map of the network. Large networks mean large maps, which means more memory and longer processing times. SPF recalculation cost. Every time something changes, routers run Dijkstra's algorithm. In a small network, milliseconds. In a huge network, you start seeing noticeable CPU spikes. And feature extensibility. As networks evolve with MPLS, IPv6, and segment routing, protocols must adapt. If adaptation is hard, migration cost skyrockets. Here's the architectural insight. IGP selection is a scalability decision, not a syntax preference. You're not choosing commands. You're choosing long-term behavior under stress. That mindset shift is everything. Now let's get into ISIS itself. ISIS and OSPF both use link state flooding, Dijkstra SPF, and identical shortest path logic. Mathematically, they compute routes the same way. Shortest path is shortest path. So what's the real difference? It's not the algorithm. It's the architecture, the structure, the encoding model, the extensibility, the operational behavior under scale. Think of it this way. 2 cars can use the same engine, but the chassis design determines performance at scale. That's the difference between ISIS and OSPF. One of the most architecturally significant things about ISIS is that it runs directly over layer 2. There is no IP header in ISIS control plane traffic. It uses CLNS for the control plane only. The data plane still forwards IP normally, but the control plane is completely independent of IP. Now, why does this matter? Let me compare. In OSPF, router A and router B must have working IP addresses to form an adjacency. If IP is misconfigured, wrong subnet, wrong mask, an ACL blocking protocol 89, or an MTU mismatch, OSPF adjacency fails. In ISIS, adjacency forms using layer 2 frames. As long as the interface is up and layer 2 connectivity works, adjacency forms, even if IP addressing is incorrect. In very large networks, misconfigurations happen. If your IGP depends on IP correctness to form adjacency, you're introducing an extra failure dependency. ISIS removes that dependency entirely. This is control plane independence from the IP layer, and it's especially valuable in large service provider cores where thousands of interfaces exist, human error probability increases, and automation may misapply templates. But there's a trade-off. Troubleshooting requires understanding non-IP encapsulation. Your operations team must understand CLNS concepts. Wireshark looks different. Packet captures look different. Debugging is less familiar, especially in enterprise teams. So the architect question is your operations team mature enough? A superior protocol that's misoperated is worse than a familiar one that's well managed. Design must match operational skill. Now let's talk about TLVs. And this is where ISIS gets really interesting from an extensibility standpoint. ISIS uses type length value structures, TLVs. Think of a TLV as a flexible container. Type tells you what kind of information it is. Length tells you how big it is. Value carries the actual information. This structure allows adding new features without redesigning the protocol. When new technologies emerged, MPLS traffic engineering, IPv6, segment routing, SRv6, FlexAlgo, ISIS simply added new TLVs. OSPF historically needed new LSA types, which required RFC updates, code updates, and sometimes operational migration steps. And in a live service provider core, protocol upgrades are expensive and risky. If extensibility requires protocol redesign, migration risk increases, downtime probability increases, and operational complexity increases. ISIS evolution historically required fewer structural changes. That's why many service provider cores standardized on ISIS. The architectural principle here: extensible control planes reduce long-term technical debt. You're designing for the next 10 years, not just today's requirement. Let's talk about hierarchy, level 1 and level 2, because this is how ISIS achieves scale. OSPF has backbone area 0 and non-backbone areas. ISIS has level 1 for intra-area routing and level 2 for backbone and inter-area routing. Here's what hierarchy is actually solving. Imagine 500 routers in one flat area. If one link changes, all 500 routers receive the update. All 500 run SPF. All 500 update their routing and forwarding tables. Now imagine 10 areas with 50 routers each. If a change happens inside area 1, only 50 routers must fully process it. That is containment. Hierarchy solves flooding containment, SPF containment, and LSDB size containment simultaneously. The architectural gain is a dramatically reduced convergence blast radius. But there's a trade-off. Route leaking and summarization complexity increases. Hierarchy reduces flooding, but it increases design discipline requirements. If summarization is done poorly, you can create black holes. Hierarchy is powerful, but misdesigned hierarchy is dangerous. In ISIS multi-level design, L1 routers know only their area. L2 routers connect areas. L1 or L2 routers bridge the hierarchy. Here's the key failure modeling question. What happens if an L2 router fails? All L1 routers that depend on it for default routing may lose backbone reachability. This is where the ATT bit comes in. The ATT bit tells L1 routers, I can reach the level 2 backbone. So L1 routers send unknown traffic toward that router. If only one L1 bar L2 router exists in an area and it fails, the entire area loses external connectivity. Blast radius equals the entire area. The design implication: Always deploy multiple L1 bar L2 routers per area. A single L1 bar L2 is structural risk. Always count your dependency relationships. Now let me talk about something I find really elegant in ISIS, the overload bit. The overload bit tells the network, do not use me for transit traffic. Here's the scenario. A router is booting. Its routing table is incomplete. Without the overload bit, other routers may start forwarding traffic through it. Traffic drops, network instability increases. With the overload bit, the router essentially says, I am not ready to carry transit traffic. The network automatically avoids it. Instead of blackholing traffic unpredictably, the network reroutes around it. The principle here, self-declaration of incapacity reduces systemic collapse. Very few protocols implement this as cleanly as ISIS does. On broadcast Ethernet segments, ISIS uses a designated intermediate system, the DIS, to optimize flooding. Without DIS, every router forms adjacency with every other router. With 10 routers, that's 45 adjacencies. With DIS, routers form adjacency with the DIS and flooding is optimized. The architect question, who should be DIS? The most powerful router, the most stable router, and definitely not a weak access device. If DIS fails, a new election occurs, some flooding happens, and temporary churn is possible. The insight, stability over randomness. Control who becomes DIS. Don't leave it to chance. Let's talk convergence engineering. ISIS convergence is influenced by hello intervals, hold timers, LSP lifetime, SPF delay, LSP refresh, and BFT integration. New engineers often think lower timers equals faster convergence. But the architect thinks differently. Lower timers means higher CPU load and more instability risk. The better approach is architectural convergence reduction through smaller flooding domains, hierarchy, and fast reroute mechanisms. Timer tuning is tactical. Hierarchy design is strategic. Never solve architecture problems with timer tweaks alone. Fast reroute, FRR, is about pre-computation as determinism. With IPFRR, the backup next hop is pre-computed and pre-installed. No SPF run is needed during failure. What's the business value? Sub 50 millisecond restoration. And that matters critically for VoIP, where jitter tolerance is low, financial trading where microseconds matter, and industrial automation where control loops are sensitive. Loop-free alternates, LFA, require no MPLS, are simple to deploy, but don't provide 100% coverage. Good for moderate SLA networks. Remote LFA requires MPLS, provides more coverage, but adds more complexity. TI-LFA requires segment routing, provides near 100% deterministic protection, and is the choice for high SLA environments. The architectural principle: FRR selection must match your SLA requirement. If your SLA tolerates 200 milliseconds, FRR may be unnecessary overhead. If your SLA demands sub 50 milliseconds, TI-LFA may be mandatory. Design must reflect business tolerance, not engineering preference. And this brings me to the final reinforcement, the mindset that ties everything together. There is no ISIS is better. There is no OSPF is better. There is only which failure model matches your business, which extensibility model matches your technology roadmap, which operational model matches your team's capability. Protocol selection is not configuration preference, it is consequence selection. When you choose ISIS, you are choosing layer 2 independence, TLV extensibility, and a hierarchy designed for service provider scale. When you choose OSPF, you are choosing broader operational familiarity, simpler troubleshooting in enterprise environments, and a widely understood protocol. Both are valid. Context defines correctness. That is architectural thinking, not what protocol to use, but what consequences you are designing for. Think in failure domains. Think in extensibility. Think in operational reality. Then choose deliberately. Thanks for tuning in today. Until next time, design with intent.